Hello all and welcome back. So in this video, let us continue our discussion on dynamic programming, and now let's try to understand the complexity of the code which we wrote in the last video. Now this technique, as I told all of you, is known as memoization. Okay. The easy way to remember it, adding memory to your recursion. Okay. So that is why it is known as memoization, where we are just making sure that we remember each and every answer of a sub problem once we have calculated that, so that it goes with respect to the overall principle or idea behind DP. Now this is the tree which we will be drawing if we try to solve our problem. So this is using plain recursion and this is using memoization. One thing always to understand and remember, everyone, that please make sure that any code which you are writing, you are able to think of the recursive solution first and then try to code the memoization or the DP approach, right? I will be giving you many problems, many such questions where you will be doing the same thing, and then overall the whole idea will become clear. The DP, the recursion code, as we saw that for let's say n equal 50, when we were calculating the Fibonacci number, it was taking a lots of time because we were solving some sub problems again and again, which when we applied the memoization technique, the same was not the case. So we were able to get the answer quickly. Now you will see here that how overall we have reduced the number of trees which are, or the nodes which are getting created, right? So all these sub trees, now you can see how exactly are they overall reduced. Let us now try to understand this complexity with the overall calls as well. So we made and calculated that how many calls are getting made. So let us compare that as well, everyone. We already have these calls. So let me just copy this overall code. All I'm doing here is just making sure or checking the calls which my DP code is making. Okay. So let us do one thing as well. What we can do, print Fibonacci number recursive. Let us call this, and along with this, okay, so for a similar way, check that, okay, how many calls overall are getting made for each and every number. Let us just redefine it. Yeah, cool. Let us run this. Yeah. So we see for 5, the answer is 8, which both of them are giving right. One call, 2, 3, 5, and 3. As we see the lower numbers, there the call is a lot high. And the reason we can see as well, right? Because these all are your base cases, and the tree for 4, only of course a single call is getting made. For 3, 2 calls. But as we keep on going down, the calls also increases for that number, because here 2 will come a lot of time, then 1 will come a lot of time, right? Let us check that for maybe say 15. Great. So here also, if we see a lot constant number of calls, either it's 1 or 2, right? 1 or 2 calls. But see here how the overall difference has amplified now. And that is the problem with the recursion code, simple recursion code. We are not overall saving our answer. That is a very big problem. Let us see for 25 and hope we get the answer. Okay. So yeah, on a magnitude of thousands of calls we are making, so 75,000 calls. But here again, you will see it's either 1 or 2. And actually these 2 are not even the calls. If I just maybe move this overall here, let's say in the DP one, if I move it after returning, right? So somewhere here, and let me do the same thing for the Fibonacci series one. Okay, here, yeah, let me just move it all down here so that the base case is not calculated, right? So that is the aim, that base case should not be calculated. Great. Cool, everyone. So this time we are not going to calculate the base case. Now let us see exactly if these 2 calls are there, exactly what is the difference. And now when we run it, you will see each and every number is getting called just one time. Because base case, again, that answer is saved. We are not doing anything there, right? It is a constant work, not dependent on anything. But still, the calls made in the recursion is a lot high. So this is a very good way. Again, we cannot visualize this thing by drawing the tree because it will be a lot more complex. I think the tool will also have some limit. So I don't want to basically make sure that it crashes. But I hope you get the idea that how exactly the recursion and memoization is helping you to optimize the code once you have transferred it to memoization. And you will see that each and everything we are just making a single call here, right? We are just making one call here for each and every number. Thus, the complexity is of the order of n, because I will repeat it again. Whereas here it is order of 2 to the power n. The reason, each and every number we are just calculating one time and then storing in a diary or memo list. Okay, so let me write this down as well. Each number Fibonacci just calculated one time, right everyone? So we are seeing this, that each number just one time we are calculating our Fibonacci and we are just storing it. So multiple saves are not there. Thus the complexity of this code becomes big O of n. The reason we are able to get the numbers so quickly, just to show you again what we can do here. If I just move this first, that is, we are just going to make the calls of DP1 of our memoization code first. And if I do it 50, okay, 1 minute. Yeah, let me run it again. Cool. So this gave us the answer. But for recursive, it's going to take a lot of time. Everything just one. So for each and every number, just doing some constant work that is dependent on number of, like how big of a number you want. So the overall complexity becomes big O of n. Okay. So that's the basic idea behind this, everyone. So I hope you're able to understand. As we move forward, we will be trying that by using some extra space, by using some memoization array, are we able to decrease the complexity of our code? That would be the whole focus which we will be having. And that is what DP majorly helps you to do. It helps you to make sure that you are able to get the answer quickly by reducing the same sub problems which you have solved before. Okay. So yeah, I hope the overall idea is clear. Again, I have made sure that I'm explaining you this with respect to the visualization, kind of how many calls are getting made, and with this tree as well. Because here, if you will see, these bolded one, they are something which have been already calculated and being get by a memo array. Okay. These non-bolded, non-filled one, they are the one which we calculate for the first time. So n plus 1 we are calculating, which is equivalent to big O of n in terms of complexity.